which is defined by a metric condition, but also closely related to the topological structure of a CBB space. So this talk is divided into two parts. So in the first half, I will talk about the relationship between extrema subsets and collapsing in CBB geometry. And in the second half, I will talk about extremal subsets in Gcva spaces, which I recently introduced. So one of the main focuses of this talk is the duality between CBB and Gcva geometries. Okay, so let's get started. So throughout the first half, I will fix an upper bound for dimension and a lower bound for curvature. So by dimension, I mean the Hausdorff dimension, and which coincides with the topological dimension for CBB spaces. Okay? And we will consider the following problem. We fix a compact CBB space X, and let M be a CBB space, in particular a Riemannian manifold that is sufficiently close to X in the Gramos-Hausdorff distance, and describe the topology of M in terms of the geometry of X. So what I mean by geometry is the singular structure of X. Okay. So this problem is very important from the point of view of Gramos' compactness theorem. So Gramos' compactness theorem says that the class of CBB spaces with curvature bounded below and with dimension and diameter bounded above is compact in the Gramos-Hausdorff topology. So theoretically speaking, you can cover this class of CBB spaces by a finite number of neighborhoods of X, as in this problem. And first, I remind you that the dimension of X is not greater than the dimension of M. And if they are equal, then Perelman's stability theorem tells us that M is homeomorphic to X. So no matter what singularity X has. So the conclusion of this theorem is very simple, but the proof is very complicated. And in this case, the topology of X, topology of M is uniquely determined by that of X. Okay. So the problem is when the dimension of X is strictly less than the dimension of M, which is called collapse. Okay. So in this case, the topology of M changes dramatically through the convergence. Okay, so for example, suppose you have a compact Lie group G of positive dimension acting on a compact Riemannian manifold M effectively and isometrically. Then there exists a sequence of Riemannian metrics on M with sectional curvatures uniformly bounded below and collapsing to the quotient space, which is a CBB space of lower dimension. So this example shows that the situation here is completely different from the theory of collapsing with bounded sectional curvature developed by Chiga, Fukaya, and Gramos. Okay. So in general, the limit space X has singular points, and there are singular fibers over the singular points. So here is a rough conjecture. So if M collapses to X, then M admits a singular vibration structure over X, and the singular fibers arise over the singular strata of X. Okay. So, and these singular strata are extremal subsets Perelman and Petroni introduced. Okay. So this conjecture was verified by several authors in low dimensions. So for example, the case where M is a three-dimensional Riemannian manifold was considered by Shioya and Yamaguchi, which contributed Perelman's solution to Poincare conjecture. Okay. So however, so far there is no theory describing the global structure of collapsing spaces in general dimensions. So my first result concerns collapsing in general dimensions. So this formula was conjectured by Semyon Areska in 2018 as a joint work with Anton Petruni. Okay. And the two-dimensional Riemannian case of this formula was recently verified by Areska, Katz, and Prozanov. Okay. So this formula basically says that the Euler characteristic of M is given by those of the strata of X and those of the fibers over them. Okay. So I'm going to explain the meaning of each notion appearing here and how to prove this formula. Okay, so let's begin with the definition of an extremal subset. Okay, so to define an extremal subset, we first introduce the notion of a critical point of a distance function. So suppose you have a point P and Q in a CBB space X. And we denote by dist Q the distance function from Q, and by sigma P the space of directions at P. And also we use this arrow to denote the set of directions of shortest path from P to Q. Okay. Then the first variation formula says that the directional derivative of dist Q at P is given by minus cosine of the minimal angle with this set. Okay. So the directional derivative in this direction is given by this angle. So we say that the distance function from Q is critical at P if this derivative is non-positive. More precisely, for any direction C at P, there is at least one direction eta from P to Q that makes an angle with Xi not greater than pi over 2. Okay, so you cannot increase the distance to Q at P. Okay, so this notion of a critical point was first introduced by Grube and Shohama in the Riemannian setting to prove their diameter sphere theorem, and later Perelman generalized it to the CBB setting. And he developed the Morse theory for distance functions. So now we can define an extremal subset. So a closed subset E of X is called extremal if it satisfies the following condition. So imagine you have a point Q outside E, and suppose the distance function from Q restricted to E attains a local minimum at P. Then P is a critical point of dist Q. Okay? Meaning that the set of directions from P to Q is pi over 2 dense in the space of directions at P. Okay? So roughly speaking, this means that the set of normal directions to E at each point has diameter at most pi over 2. But this condition is very technical, so let me give you some examples. So first, the boundary of a CBB space is extremal. So here the boundary is defined inductively in such a way that P is a boundary point if and only if its space of directions has no empty boundary. And another example comes from group actions. So suppose you have a compact group G acting on a CBB space M by isometries. Then the quotient space is a CBB space with the same lower curvature bound, and the projection of the fixed point set to M over G is extremal. Okay, and actually this holds for any subgroup of G. Okay, so in particular, if M is a Riemannian manifold and if G is a Lie group, then, as I said, M can collapse to M over G, and the fixed point set forms an extremal subset of the limit space. Okay. So now we are going to describe the stratification of CBB space by extremal subsets introduced by Perelman and Petruni. So we say that extremal subset is primitive if it is not covered by its proper extremal subsets. Okay. So primitive extremal subset is, in a sense, a minimal extremal subset. And the main part of a primitive extremal subset E is the relative complement of all proper extremal subsets in E. So, for example, if you have a square, then each vertex and each edge are primitive extremal subsets. However, the boundary is an extremal subset, but not primitive, because it is covered by these edges. And the main part of this edge is the interior of this edge, okay? And what Perelman and Petruni proved is that any CBB space is uniquely represented as a disjoint union of the main part of primitive extremal subsets. And moreover, they proved that these main parts are topological manifolds. So this gives a stratification of a CBB space into topological manifolds. So that's why this subset is very important in CBB geometry. Okay. Okay. So now we get back into the collapsing situation. So suppose a CBB space M collapses to a compact CBB space X. And here we recall two vibration theorems due to Yamaguchi and Perelman. So Yamaguchi's vibration theorem is that if both M and X are Riemannian manifolds, then there exists a locally trivial vibration from M to X, which is actually an almost Riemannian subversion. Okay. And I'd like to point out that the assumptions on M and X have completely different meanings. Okay. So basically, you can remove the assumption on M, but not on X. So let me explain. So here is generalization of this theorem to CBB spaces. So suppose M and X are CBB spaces, and let delta X be the Spreeman of the Gromov-Hausdorff distance between the space of directions X and the unit sphere. And let epsilon M be the infimum of the volume of the space of directions of M. And if delta X is sufficiently small compared to epsilon M, then we obtain the same conclusion, that is, locally trivial vibration exists. Okay. And so this condition means that X is close to a Riemannian manifold, and the singularities of M are not so bad. Okay. And it is still an open problem whether you can remove the assumption on M completely, but I will not go into this problem because it is not related to extremal subsets in the limit space. Okay. So the connection between extremal subsets and collapsing was first observed by Perelman. So he proved that if X has no proper extremal subsets, then M admits a self-vibration structure over X in a weak sense. So I will not explain what this exactly means, but this is a sort of homotopy lifting property for simplicial complexes. Okay? And in particular, there exists an exact sequence of homotopy groups of M, X, and a fiber. Okay, so there is still a weak vibration structure. And the conclusion of Feynman's theorem is weaker than that of Yamaguchi's theorem, but the assumption is optimal. And what we are going to do here is to extend Feynman's argument to a general limit space, which means that we do not assume any regularity condition on X. Okay. So to state our main theorem, we record the notion of a good covering of a CBB space introduced by Mitsuishi and Yamaguchi. So let X be a compact CBB space, and we first record the following theorem due to Feynman and Petruni. So for any point P, there exists a strictly concave function around P with a unique maximum at P. Okay. So a distance function from a point in a CBB space is semi-concave by definition, and they applied some averaging technique to distance functions from points around P to obtain this strictly concave function. So this strictly concave function is basically defined by distance functions. So if there is a converging, if there is a space converging to X, then you can lift it to that space. Okay, and Mitsuishi and Yamaguchi defined a good covering of X by a finite open covering U whose element is a super-level set of a strictly concave function of Feynman and Petruni. Okay, so this covering is good in the usual topological sense, but also has many nice geometric properties. Okay, so let NU denote the set of non-empty intersections of elements of U. And they proved that any such non-empty intersection is Lipschitz contractible. So Lipschitz means the homotopy is a Lipschitz map. And actually this homotopy is given by the gradient flows of semi-concave functions. And such gradient flows preserve extrema subsets. So this covering is in a sense compatible with extrema subsets. Okay. And they also proved that X has the same Lipschitz homotopy type of the nerve of U. And this implies that the Lipschitz homotopy stability of non-collapsing CBB spaces, which means that if you have two CBB spaces of the same dimension that are sufficiently close in the Gramos-Hausdorff distance, then they are Lipschitz homotopy equivalent. So this gives another approach to Lipschitz stability Feynman claimed. But here we are going to apply this covering to collapsing situation. Okay, so now we can state our main theorem. So suppose M collapses to X, then there exists a press sheaf on a good covering U of X such that F is locally constant on the main part of a primitive extrema subset of X. And also the spectral sequence associated with F converges to the cohomology of M, where we fix a coefficient field. So let me explain the meaning of this theorem. So the precif F is a functor from the nerve of U to the category of groups. And actually F assigned to each element of the nerve the cohomology group of a natural lift of U to M. Okay, so a good covering is defined by strictly concave functions, and strictly concave functions are based on distance functions, so you can lift it to M. And what this condition 1 means is that, so let EU denote the minimal extremal subset intersecting U, which always exists. Then this condition 1 means that f of u is uniquely determined by this extremal subset EU up to isomorphism. More precisely, if u is contained in another element v of nu, and if EU is equal to EV, then the induced homomorphism from FV to FU is an isomorphism. Okay, so this is our main theorem, and this is proved by extending Perelman's argument to each primitive extremal subset in X and combining it with the properties of a good covering. Okay, so, and I should mention that there is a related but unpublished result of Petrini found in the paper of Areska, but I don't know the detail, sorry. And so now you can calculate the Euler characteristic via the spectral sequence given by the main theorem to obtain this formula conjectured by Areska. So the Euler characteristic of M is given by the sum of the products of the Euler characteristic with compact support of the main part of E and the Euler characteristic of a regular fiber over E. So what I mean by a regular fiber is that, so you take an arbitrary point P from the main part of E, then there exists a small radius such that the distance function from P has no critical points on the ball of this radius. And you lift it to M, and then it gives a regular fiber FE. And it turns out that the homotopy type of a regular fiber does not depend on the choice of P, and it only depends on the extremal subset E. Okay, so in particular, the Euler characteristic of a regular fiber is well defined, so this formula makes sense. Okay, and let me finally mention that Areska's conjecture is not only about the Euler characteristic, but also about the intrinsic volume of Riemannian manifold. For example, the integral of the scalar curvature. Okay, so I cannot explain his conjecture here, but the Euler characteristic is a very special case. So I hope this helps to prove the general case of his conjecture. Okay, so this is the first part of my talk. Are there any questions so far? Okay, so let's move on to the second topic, extremal subsets in GCBA geometry. So in general, the structure of CBA spaces is much more complicated than that of CBB spaces. So for example, the Hausdorff dimension may be bigger than the topological dimension for CBB spaces, which does not happen for CBB spaces. Okay. So to obtain some control, we will consider GCBA space, which means a geodesically complete CBA space. So the theory of GCBA spaces was developed by Richak and Nagano, and it has many similarities with the theory of CBB spaces. So from this point of view, I will introduce the notion of an extremal subset in a GCBA space and describe its basic properties, especially its connection with the topological structure of GCBA space. Okay, so let's begin by defining a GCBA space. So we say that a CBA space is locally geodesically complete if any geodesic is locally extendable. So here, geodesic means a locally shortest path, as in Riemannian geometry. And a GCBA space is a separable locally compact and locally geodesically complete CBA space. So let me give you some examples. So let X be a CBA space such that for any point P, sufficiently small punctured ball around P is non-contractible. Then X is locally geodesically complete. So if X is a topological manifold, then this assumption means that X has no boundary. Okay, and more generally, this assumption is satisfied by any homology manifold with a CBA metric. And the next example is called Restoniak's gluing theorem, which says that if you have two GCBA spaces, x1 and x2, and if there exist isometric closed locally convex subsets C1 and C2, then you can glue x1 and x2 along C1 equals C2 to obtain a new GCBA space. Okay. So in particular, the convex subset will become a singular set in the glued space. Okay, and before discussing extremal subsets, let's briefly recall the results of Richak and Nagano. So let X be a GCBA space. We denote by TP the tangent cone at P, and by sigma P the space of directions at P. So they are well defined and they are GCBA spaces. And first, they proved that the Hausdorff dimension of X is equal to the topological dimension of X. So the dimension is well defined, and so we can define xk as the set of points whose tangent cone has dimension k. So as I said, the tangent cone is a GCBA space, so the dimension is well defined. Then the Hausdorff dimension of xk is k, and xk contains an open dense Lipschitz K manifold with codimension at least 1. Okay, so the local dimension may not be constant, but each k-dimensional part of X contains an open dense Lipschitz K manifold. Okay, and the next theorem is called the topological irregularity theorem, which characterizes a manifold point in a GCBA space in terms of the tangent cone, the tangent cones or the spaces of directions around it. Okay, so this theorem says that X is a topological manifold if and only if any tangent cone is homeomorphic to Rn, or any space of directions is homotopy equivalent to Sn minus 1. Okay, and so note that this homotopy equivalence cannot be replaced with a homeomorphism. Okay, so there is a counterexample from geometric topology. So suppose you have a homology sphere, then its suspension is not homeomorphic to a sphere, but its double suspension is homeomorphic to a sphere. Okay? So in particular, if you consider the space of directions of this double suspension at this pole, then it is a single suspension of the homology sphere. So this is not homeomorphic to a sphere. Okay. And I'd like to note that these theorems also hold for CBB spaces. So you might think that GCBA spaces have a similar structure to CBB spaces, and this is partly right, but partly wrong. So the singular structure of GCBA spaces is much more complicated. So for example, GCBA spaces do not admit any stratification into topological manifolds like CBB spaces, which was shown by Kleiner. Okay. However, we can still define extremal subsets and find some connection with the topological structure. So to define an extremal subset, we first introduce the notion of a critical point of a distance function in GCBA geometry, which is dual to the critical point of Grove, Shiohama, and Perlman in CBB geometry. So first note that any point of a GCBA space has a compact convex cat neighborhood U. This immediately follows from the definition of a GCBA space. And for any point P and Q in U, we denote by this arrow the direction of the unique shortest path from P to Q. So here, the uniqueness flows from triangle comparison. And we will consider the set of antipodes for this direction. Okay. So here is P and here is Q. And here is the direction from P to Q. And we are looking at this set. And this subset is non-empty because of geodesic completeness. So you can always extend the shortest path from Q to P to some extent. So there is at least one opposite direction. Okay. And we say that the distance function from Q is critical at P if for any direction Xi at P, there is at least one direction eta opposite to the direction from P to Q, such that the angle between them is not less than pi over 2. Okay. So this means that the branching angle at P of this shortest path is somehow large. Okay. And here is the definition of a critical point in the CBB setting that I gave earlier. So instead of considering the set of directions from P to Q, we consider the set of antipodes for the unique direction from P to Q. Okay. So you can find some duality between these two definitions. Okay, so now we can define extremal subsets almost the same way as before, except for the definition of a critical point. So a closed subset E of X is called extremal if any point E has a neighborhood U where we can use triangle comparison in X, such that if the distance function from Q restricted to E attains a local minimum at P, then P is a critical point of dist Q, which means that the set of antipodes for this direction is large. Okay. So a basic example comes from Restoniak's Green theorem. So suppose X is a grouping of two GCBA spaces X1 and X2 along C1 equals C2, where Ci are closed locally convex subsets of Xi. And suppose the topological boundary of C1 is equal to that of C2, then the convex subset itself and also its boundary are extremal subset in the Gould space. Okay. So as you can see here, many geodesic branch on this subset. Okay. And in particular, any closed locally convex subset of a GCBA space and also its boundary can be viewed as extremal subsets in the doubled space. Okay. This is due to the fact that the boundary of a CBB space is extremal. Okay, so Now we are going to describe a connection between extremal subsets and the topological structure of a GCBA space. So let X be a GCBA space, and we denote by xk home the set of points whose space of directions is homotopy equivalent to sk minus 1, and by xk top the set of points having a neighborhood homeomorphic to Rk. Okay. Then xk top is contained in xk home, and the equality here holds if and only if xk home is open. So this is a consequence of the topological irregularity theorem of Richak and Nagano that I mentioned earlier. And if this assumption is satisfied, so if xk home is open, or equivalently if xk top is equal to xk home, then its complement is an extremal subset of X. Okay. In particular, any isolated non-manifold point of X, for example, any singularity of a CBA homology manifold is an extremal point. Okay. And so let me talk a little bit about this assumption. So, so this assumption is satisfied for at least k equal 2. And as far as I know, there is no counterexample. And Professor Nagano told me that this assumption is the problem that he has been trying to prove for many years. So I hope this is true, but the proof will be very difficult. And the difficulty here is that xk home is defined by the infinitesimal structure, whereas xk top is defined by the local structure. And I think this is not known even for CBB spaces. Okay. But you can ask.
Sorry, can you say that again? What is not known for CBB spaces?
I think this assumption is not known even for CBB spaces. Okay. But you can ask a little bit easier question of whether the complement of xk top is extremal. And this is known for CBB spaces. But I also, I'd like to point out that the proof of this fact for CBB spaces uses the theorem of Perelman, which says that any point of a CBB space admits a metric neighborhood homeomorphic to its tangent cone. And this kind of strong connection between the local and infinitesimal structure does not hold for GCBA spaces. So that's why this problem is more difficult than the case of CBB spaces. Okay, so I will conclude my talk with the structural properties of a general extremal subset in a GCBA space. So first, we see that the Hausdorff dimension is equal to the topological dimension for an extremal subset of a GCBA space. And it also equals the maximal dimension of open subsets in E that are by Lipschitz homeomorphic to Euclidean balls. Okay, so the dimension is well defined. And actually, the same holds for any open subset of E. So this enables us to define the local dimension of E at P by the limit of dimensions of R ball around P in E. Okay. And you can also define the infinitesimal dimension of E at P by the dimension of the tangent cone of E at P. So the tangent cone of an extremal subset is an extremal subset of the tangent cone of the ambient space. So the dimension is well defined. Okay. And the local dimension is not less than the infinitesimal dimension, but the equality does not always hold. Okay? This is different from CBB extremal subset. And this is again the gap between the local and infinitesimal structures of Gcva spaces. And let Ek be the set of points in E with local dimension k. And let Xk regu be the set of k regular points in E, meaning that the tangent cone is isometric to Rk. And note that Ek regu is not necessarily contained in Ek for the same reason as the previous remark. Okay, so Ek is defined by the local structure, whereas Ek regu is defined by the infinitesimal structure. But you can show that the intersection of Ek regu and Ek is dense in Ek, and also the complement has Hausdorff dimension at most k minus 1. Okay? So each k-dimensional part of E contains sufficiently many k-regular points. And also the k-dimensional Hausdorff measure is locally finite and locally positive on Ek. Okay. And for the manifold structure of extremal subset, we obtain the following theorem. So Ek is k rectifiable, meaning that Ek is covered by a countable family of the images of Lipschitz maps from subsets of k-dimensional Euclidean space up to a set of measure 0. And also Ek contains an open-dense Lipschitz k manifold. Okay. So you might expect that the set of k manifold points in Ek has full measure, but this is not the case. A counterexample was constructed by Nagano, Shioya, and Yamaguchi in dimension 2. The picture looks like this. This is a variant of Kleiner's example of a Gcva space that admits no stratification. So this is basically the gluing of two planes, but the gluing subset is much more complicated. Okay, and this is again different from CBB extremal subset. Okay, so in conclusion, extremal subsets in Gcva spaces do not have nice properties as extremal subsets in CBB spaces, but they still have some connection with the topological structure. So I think they are worth studying. Okay, so I think I'll stop here. Thank you for listening.